The last thing I want to do in this unit is introduce to you the so-called atomic units. And this is part of the reason I included this description of the Bohr energy levels, because that relates to talking about the atomic units. So basically, when you look at the equations, you see that they are for like energy levels and potential energies and such in hydrogen-like atoms. You see that they're exceedingly complex, and it's just simply because there's a whole big collection of constants in there, and that complexity, that whole big collection of constants, kind of masks the underlying simplicity of the whole thing. So people who do theoretical and computational chemistry, to avoid all that, they very commonly use a set of units called atomic units. Atomic units are defined by setting certain constants equal to exactly 1. And these are h bar. H bar is, in atomic units, is exactly 1. The mass of the electron in atomic units is 1. And finally, the whole thing regarding the attraction between unit charges, charges with charge equal to the electron charge, and defined in the equations as E squared over 4 pi epsilon naught. In atomic units, the force between charges is defined in such a way that this quantity is also equal to 1. It may not be obvious, but just believe me when I say it, that you can come up with a consistent set of units in which you can set these particular constants equal to 1. So to see how it simplifies things, let's go back and look at the formula for the potential energy in a hydrogen-like atom, a nucleus of charge Z, and an electron. That potential energy is given by this equation. So V is Z E squared over 4 pi epsilon naught R. So you can see if E squared over 4 pi epsilon naught is exactly equal to 1, this whole part in the equation here, the formula for potential energy is simply minus Z over R. So then continuing, we looked at the energy levels one gets when one has a quantized value of the angular momentum. And the first thing we saw was that only certain radii were allowed as a function of the quantum number n. And the formula for R was given by this equation. And you can see that if we do atomic units, we see the h bar squared, which I'll circle here. That's equal to 1. This part involving the charge of the electron and the 4 pi epsilon naught, that's equal to 1. And this is equal to 1. So in atomic units, the allowed radii simply come out to be n squared over Z. And then also, continuing on, we saw that the radius of the lowest energy of the hydrogen atom, which we called A0. I won't write this all down, but that Bohr radius in atomic units, A0, is also equal to 1. And then finally we look at the equation for the energy levels, the quantized energy levels, as a function of the quantum number n, given by a rather complicated expression. Here, you look at all the constants in here, we see this is equal to 1, this part, take those together, those are equal to 1, the mass of the electron is equal to 1, and we simply have the energy levels are given by minus z over n squared. Excuse me, minus z over 2n squared. So when we look at the hydrogen atom specifically, and we look at the lowest energy level of the hydrogen atom, we will have energy is minus 1/2, and the electron was moving in, according to the Bohr model, is moving around the atom in a circle of fixed radius r equal to 1. That's the Bohr radius in atomic units. And incidentally, when we do the quantum hydrogen atom, where we don't have this fixed radius, A0, this will be the average distance of the electron from the nucleus. And at this distance, at the fixed radius for the hydrogen atom, we will have that at that radius, V is equal to minus 1, and of course the kinetic energy is equal to plus 1/2. In atomic units, the energy unit is commonly called the Hartree, or it's also just abbreviated. Sometimes you'll see E equals, like minus 0.5 AU for atomic units. AU, atomic unit of energy, is the same thing as the Hartree. So the energy is in Hartrees. Distances are in units of the Bohr radius. So you can think of A0, the Bohr radius, as being our basic unit of distance in atomic units. So I think you can see that expressing things in atomic units can make a lot of these equations much simpler, and when we do the hydrogen atom, the full quantum picture of the hydrogen atom, we will stick to atomic units. And then the conversion between, I included Hartree in my energy unit conversion, and in the sheet I gave you on the electromagnetic spectrum, I included Hartree as another unit. If you want to do some more manipulations in kind of normal SI units, just convert the energy that you calculate in Hartrees into say joules or whatever you need, and then go from there. And the conversion is given in the conversion spreadsheet that I posted for you. So finally, let me say something about the problems I asked you to do at the end. I said find the velocity of the electron in the n equals 1 and 2 states of the Bohr hydrogen atom and express in meters per second. Well, to me, the easiest way to do this problem is to first write the relevant energies in atomic units, and we have E equals, and then for a hydrogen atom, minus 1 over 2 n squared. In the n equals 1 and n equals 2 levels, that's minus 1/2 and minus 1/8. The kinetic energy is, so the kinetic energy is plus 1 over 2 n squared. Just remember, this comes from the virial theorem. So that is plus 1/2, and remember that's Hartree, and plus 1/8. And the radii of these two atoms is R, in atomic units, is R is equal to n squared when z is 1. So R is 1 or 4. And so basically I can convert, use the conversion I gave you to convert these to from Hartree to joules. R is 1 or 4, and that is A0 for the n equals 1 level, or 4A0 for the n equals 2 level. You can look up a value of A0, the Bohr radius, in a table of fundamental constants and get that in meters. And then go from there. You'll have R in the radius of this circle in meters. You'll have the kinetic energy in joules. And then you can go from there to find the circumference of the circle, the various things about that. You can find the velocity of the electron in these two states, and you can also go from there and calculate what I ask you to, the orbital period and the number of orbits per second in these two states. So at any rate, that concludes my my introduction to the classical hydrogen atom, and I just want to emphasize that this is a really crude and not entirely correct classical picture, but it does allow us to look at some of the quantities involved and introduce the atomic units, which are going to be very important when we look at the full quantum treatment of the hydrogen atom.